All right. Well, welcome everyone to what I guess is lecture 5 already. It's been running very fast, and so let's recap a little bit where we stand with the course. So our goal, and I guess in quantum field theory in general, is to develop some understanding of quantum field theory, which is completely independent of perturbation theory. So eventually you want to kind of bring quantum field theory to the same status as the theory of finite dimensional algebras or groups, where you can write down some sort of axioms and classify the objects, classify quantum field theories, and eventually also compute as much as you can in those quantum field theories directly from the axioms. And that's of course an important research program which has been ongoing for a while. And what we are focusing on this course is an instance of this program in the case of fixed points of the RG flow. So these are conformal field theories which have postulated to have some symmetry that we talked about over the last 2 lectures. So there are these generators. Okay. Now the objects, in the analogy, if we were classifying groups, then we would be talking about group elements and their multiplication table. So what is the analog of the group elements and the multiplication table? Well, in this case, it's the local operators, OI, which live in some position in RD. And the kind of data that we want to understand are the correlation functions of these local operators. So we can think of this either as a kind of a statistical sum in a lattice model and a continuum limit, or a path integral. So these are some operators which commute with each other. Okay, and we want to understand these correlation functions in RD. And then in conformal field theory, there's an important idea that you can map to the cylinder. So you can map to the cylinder from RD. To the geometry R times SD minus 1 using this map where the coordinates on the cylinder go to e to the tau times n, where so tau is in reals and n is on the sphere. So, okay. But there's an important small subtlety which I kind of skimmed over the lecture so far, which is that if you take the same the same local operators and compute their correlation functions in the plane or in RD and on the cylinder, then you're going to get a slightly different answer. And the reason is that we are performing a conformal map between the two, and there is a non-trivial conformal prefactor, a non-trivial conformal factor, which is basically the metric on the cylinder. On the SD minus 1 is equal to the metric in RD only up to a factor which is e to the minus 2 tau, right? So basically, as you go very far in RD, this sphere gets bigger, but here the sphere doesn't get bigger as we keep going up. So we need to compensate for it by this factor, and correspondingly, because we are doing some local rescaling, and these local operators, they can feel the rescaling. So that means that the correlation function in the plane is related to the correlator on the cylinder by some non-trivial factor coming from each operator. So the correlation function on the cylinder now, so let's do the same. So now let me label the same operators by their position on the cylinder. So I'm using the cylinder time and the sphere location. Okay, well, I guess this little n is different from that number of operators. So unfortunately I have nn. Okay, let's just call it capital N then. And if we compute this on the cylinder using the same local operators, then we need to insert this factor, which corresponds to the fact that we are so now we are going to compute a correlation function in RD instead of on the cylinder, and we are inserting the operators at at the corresponding locations in RD. So this should be I1, and this should be IN. So it should be tau 1 and tau n. Okay. There is an O missing. Tau n, and this is computed in RD. Okay, and okay, now yeah. Now because we have a situation where the geometry is r times a manifold, we can quantize, so we can introduce a Hilbert space, which we called V, and that we decomposed into irreducible representations. So then we had these irreducible representations, which are labeled by scaling dimension and rho. So this is the scaling dimension, which is some real number, and this is an irrep of SOD, which is usually called spin of the operator. And then we can represent this correlator on the cylinder as a matrix element of a product of operators, right? So this is the usual way that path integral gives rise to Hilbert spaces and operators acting on them. So to each operator on the cylinder, we can associate an operator in the literal sense of function analysis. So let me put a hat. And this correlation function is then computed as a matrix element of a product of these objects. Actually, let me be careful. But it's important that they are radial ordered now. Okay, so what this does is that it looks at all the times, the Euclidean times, and radial orders them. The reason, of course, is that this object is the same as either tau d, oi, on, e to the minus tau d, and you're only ever allowed to multiply these things together if later time comes after earlier time, right? Otherwise, you're going to be dealing with things like that. So this is an operator. Right? This is an operator acting on our Hilbert space, which is only really which is only bounded when tau 1 is greater than tau 2. So if you do things correctly, you will never see. You will never encounter a situation when tau 1 is less than tau 2. Right? This would not be a good operator in that case. Yeah. So in this picture, everything commutes. So these are not operators in a sense of function analysis. They are just probes into the path, and like something that you insert into the path. Like everything, just like numbers, basically, just commute. Well, they're functionals of the fluctuating fields. Here, they are quantum operators, so they definitely don't commute, and actually, their product only makes sense if they are ordered in a correct way. Otherwise, it doesn't even make sense. Otherwise, and then very interesting things happen when you continue to the Lorentzian signature. So once you do this, tau goes to IT. Then this object starts making sense for both orderings because now it's oscillating, and that means that in Lorentzian signature, you can consider correlation functions which are out of the Lorentzian time order. But in Euclidean signature, you cannot. Okay, so yeah. Yeah, so here, that one are the coordinates on the cylinder. It's the same operator. So it's a, yeah, for me, D, I guess D hat or D is the quantum operator, which is the cylinder Hamiltonian. Yeah. Yeah, they're just physically meaningless because the Euclidean correlation functions are permutation invariant in these ones, and the only way to compute them using matrix elements of products of operators is if you radially order, right? So if you radial order the times, so if you order the times or radial order the radii, which is the same thing. Sorry, you want to start with this? Okay, let me. Okay, what you're suggesting is a good suggestion, but it's a bit complex. I don't want to get too deeply into this Euclidean Lorentzian, but it's good. Yeah. Let's. Okay, so and so local operators corresponding to this of course starts with the vacuum. So the trivial representation, which is delta equals 0, and trivial SOD. So this is when I was denoting the vacuum. And then there's an infinite sum of irreducibles later on. So every conformal field theory comes with its spectrum. So this is the set of deltas and rhos is the spectrum of the theory, the spectrum of local operators or states on a cylinder. And we'd like to understand what kind of spectra are allowed in a completely non-perturbative way. I want to make sure that I don't skip something important. Okay. And the way to constrain the spectrum is to realize that there is a certain multiplicative structure on the set of operators, which is called the OPE, or the upper product expansion, which we'll get to in a second once we discuss correlators a little bit more. So let's get a little bit more intuition about these correlators in RD. So we had our conformal generators. So now let's just think of them as these charges wrapping our Euclidean operators, commuting Euclidean operators in RD. So we had these formulas. Let me not write M because we are not even going to use it explicitly. So K, acting on that. Sorry, yes. And then I know M. I already wrote everything yesterday, so probably. Okay, and let's now use these to constrain correlation functions. And let's go back to RD, sort of a cylinder. So if we have one of these generators, so let's call it A. So A is one of these generators. and we act, so the statement that the theory is invariant has a consequence that correlation functions satisfy word identities. So let's do it like j from 1 to n, which means that if we act with each of these generators on each of the operators, we have to get 0. So we have the first operator in the first location. Then our generator acts on the jth operator. Okay. So that's these are the so-called conformal word identities, which are, from the point of view of this quantized picture, they are a consequence of the fact that all of these generators, so I should say, okay, we can of course think of these charges as wrapping the cylinder, like that. So now the codimension thing, one thing is located along the spatial sphere, and then it acts as an operator acting on our Hilbert space. That's of course how we got this representation. So we can call these charges with hats, and so on. And these statements that correlation functions are invariant under the conformal transformations, they are a direct consequence of the fact that these quantum charges annihilate omega. So, well, let me just. So there is a set of these charges, the conformal charges, and we have a set of corresponding quantum operators, each of which annihilates omega. Right, so if you take this statement in these matrix elements, you translate it back to the statement about correlation functions, you find these identities. So this is kind of a more or less standard stuff from quantum field theory, so let me not explain it in more detail. And let's now just apply these identities to constrain the correlation functions. And by the way, whenever I write O, I mean the primary operator. So it's the state that corresponds, it's the operator that corresponds to the lowest weight state in this representation, well, which I erased already. Okay, so I should have said that OI of X is a primary operator. From now. And I'm going to focus on the case where all of these OIs are scalar. Focus on scalars, meaning that rho I is the trivial representation, but I'll make some important comments also for the more general case. Okay, so let's start. The first, of course, is the 1-point functions. So we have P, D, M, and K. So if we use P, if we use this invariance, we get it that it's a constant, and we already saw that if we use D, then we find that C is 0 unless delta is 0, delta I is 0. So we already saw that in the previous lecture, the first lecture yesterday. So we are just using scale invariance. Okay, so that's the 1-point function. Now the 2-point function, yeah. Well, so yeah, you get contact terms when you write ordinalities using the currents. So here I'm not using the currents; I'm using the integrated currents, so the charges. So none of these x's are the same position. That's an important comment. Yeah, all of these local operators are at different positions, and the current is integrated over a surface which doesn't touch any of the operators. So that's this A. Thanks. Okay, let me maybe leave that. Yep. Well, yeah, but sorry. I mean, in this formula, there is a bunch of x's, and none of these x's are ever at the same point. So any delta function, but so the contact terms which are important in word identities are those between the current and the local operators. That never happens here because the current is integrated over a surface that never touches the operator. I mean, yeah. So I mean, this is correct. We can discuss more. I mean, of course, contact terms are important to understand word identities, but okay. So now 2-point functions. We already saw that if we use scaling, so if we use translations and scaling, then the 2-point functions would have to look like some constant divided by delta I. Sorry, so this uses translations, rotations. So I'm using translations to write as a function of x1 minus x2, then rotations to write it as a function of the norm of x1 minus x2, and then I'm using scaling to show that the function of the norm has to look like that. But we haven't used k, so we haven't used a special conformal transformation, and it turns out, so this is an exercise that everybody should do if you haven't done it, is that applying k, ka, implies that Cij is 0 unless delta I is equal to delta j. Okay, so this is not really obvious. I think you have to do the calculation. Just apply this differential operator in this way. So there's going to be one term from this operator, another term from this operator, and you get a contradiction unless the two deltas are the same. Okay, so we can write it as a, well, I guess I should keep Cij for now, but here we know delta is equal to delta j. So there's going to be 2 delta I. And now furthermore, okay, so what is Cij? So Cij is some symmetric matrix, which if we are working with real operators, so it's a real symmetric matrix. And in a unitary theory, it also has to be a positive, definite real symmetric matrix. Because this 2-point function is basically the inner, I mean, it's related to the inner product. So Cij is a real symmetric positive definite matrix. So meaning that all of its eigenvalues have to be positive. And then we can just diagonalize it. So we can choose a basis for these operators such that it becomes delta ij. So we will diagonalize it. So that Cij becomes delta ij, right? So any real bilinear form, any real symmetric bilinear form can be diagonalized over the reals, and its only invariant is the signature, like the number of pluses, number of minuses. Now we are saying that it's positive definite, so there are no minuses, it's just pluses, so it's this delta ij. Okay, so we are going to use that from now on. So now it's really manifest that this 2-point function is like the inner product, and we are working in the basis. We are working in the basis where the inner product is diagonal. And the same thing is also true for spinning operators. So when rho is non-trivial, there is just a more complicated. So the 2-point function looks a little bit more complicated, but it's still uniquely fixed. Well, you can just choose you can always rescale the operators, right? So we are for it to be 1. There is no normalization. I mean, yeah. You can, there's a difference between linear transformations and bilinear forms. And for linear transformations, you cannot change eigenvalues by conjugation, but for bilinear forms, you can rescale. And this is not a linear map. This is a bilinear form. Okay. So yep.
What is the second part necessary? Because if we just apply K, then we show that Cij is 0 unless delta is equal to delta J, right?
Mm-hmm.
So surely like that must be enough to say that Cij is like delta J.
Good. Yeah. So why did I? Well, it's because there could be multiple parameter operators with the same scaling dimension. Okay, so yeah, if I don't make these comments about diagonalization, then there could be some finite number of operators of the same dimension. Yeah. Okay, well, I guess we have that. Okay, so this is basically the first point, first point in time, where you see that conformal is stronger physically than just scale, because with scaling symmetry, we couldn't reach this conclusion that delta has to be equal to delta J, and things get better once you look at the 3-point functions. So now, if you look at 3-point functions, let's call it OI. I guess let's call it OI, OJ, and OK. Okay. So if we use translations only, then it has to depend on these two vectors, x1 minus x2, x1 minus x3, say. Now, if you use rotations, then it has to depend on their norms, on the norms of these two vectors, and maybe also their inner product. So basically, it has to depend on 3 numbers. So it's a function of three variables. Now, if you use scaling, that eliminates one of those variables. So you basically using P, M, and D, you can reduce to a function of 2 variables. I mean, why is that? Well, it's because there are 2 translation, scale, and rotation invariant quantities, which are these quantities, right? The x1 minus x2 over, actually, sorry, let me introduce notation where xij is xi minus xj. And then there are 2 quantities which it could in principle depend on, which is this, and I guess that. Right, so both these are translation, scale, and rotation invariant quantities. So we could only ever determine a 3-point function up to an unknown function of 2 variables. But it turns out that using special conformal generators, you can actually fix this function completely up to an overall number. And this was actually done in the first paper by Polyakov. So this is kind of where Polyakov realized, conformal symmetry is really powerful because it fixes the 3-point functions. And so what's the answer? So if we use K, then we find the following beautiful formula for the 3-point function. Okay, I think, let me just, okay, just going to, the equal sign goes up. So it's delta I plus delta J minus delta K, and x13 delta I plus delta K. Okay, I already see I'm running out of space. Sorry, so let me just write it. Let me write it on a different board because it's an important formula. Okay. Yeah. So this function of of two variables is completely fixed. Again, well, it's an exercise. Now, why could have we expected that? There's a simple mathematical reason why the conformal group is powerful enough to fix the 3-point functions, and that's basically because we can use the conformal group to move any 3 points to any 3 other points. And so we can, if we allow ourselves to use the inversion, so suppose we start with 3 points. I can write it over here. So if you have 3 points, x1, x2, x3 in RD, then you can use the inversion. Say inversion around x3. So inversion around x3 is going to map x3 to infinity. And now you can still use all of the transformations which preserve infinity, so translations, rotations, and scaling. So you can now still translate x1 to the origin, say. Translate x1 to the origin. So now we have x3 at infinity, x1 at the origin, and x2 is somewhere. And you can always rotate so that x2 is on any particular axis that you want, and then rescale so that x2 is at any distance that you want. So, for example, so we can rotate and rescale to send x2 to the unit vector in any direction that you want. So let's say E1. Let's say E1 is the unit vector in direction 1. And if you want to avoid inversion, you can also, if you want to just use the connected component of identity in the group, then you can just use special conformal instead of inversion here to map x3 to infinity. Okay, so that's why. No, so and of course in this process, you're going to pick up some rescalings that the operators can feel, which is why if you kind of retrace these factors, the rescaling factors back, you get this particular dependence on x1, x2, x3. Okay. Are there any questions? Mm-hmm. Well, I'm glad you asked. That's what the rest of today will be about. Okay, so what are these coefficients? So remember, We are working with real operators, so these are some real numbers. But for now they are free. But in general, they are not free, as we will see. So these are real numbers, which are fully symmetric in this case. Okay, so in the CIJK, it's equal to C any permutation of IJK. Right. So sigma is an element of the permutation group of 3 letters. Okay, I guess I should go here now. Okay, so with this preparation, I can finally tell you about the OPE, or the operator product expansion. Okay, well, so the rough physical idea is that we have some complete set of local operators, right? And if we draw 2 operators some distance away, if you kind of keep zooming out, you're going to see that they approach each other and they start looking like a local operator, just like a single local operator. So let's call this O1 at X and this O2 at Y. Maybe OI, OJ, sorry about that. No. Right. So there should be a sense in which we can just replace this product of 2 local operators by some infinite series of local operators at a point, just because we have some complete set of local operators. Now this would be nice if one could make it precise, but in general quantum field theory it hasn't been made precise. But in conformal field theory you can make it precise because you have the notion of a Hilbert space, right? When you have a Hilbert space, that means that you have a spectral decomposition of the Hilbert space, and you can use, so that there's like a well-defined notion of convergence of infinite sums because you have the norm. So it can be made totally precise. So the way to think about it is that we'll do radial quantization around this OJ. Right. So we have OJ at Y quantized on a unit sphere. So this is sphere centered at Y of unit radius, unit sphere. And then for all practical purposes of computing any correlation functions, OJ at Y is equivalent to just to the state OJ, right? So this is the lowest weight. This is the lowest weight state in our representation delta J, 0, or trivial, sorry. And OI of X is just some operator acting on it, right? So now this is now just a state, right? So when we look at the sphere, we have used this picture just corresponds to a particular state which depends on X minus Y and I and J, but it's a state in a Hilbert space, so we can expand it in the basis of our Hilbert space. Okay, so this is just some vector in V. So the idea is to just expand expand it in the basis. And the main thing, of course, to remember is that the V is a direct sum of irreducible representations. Okay, so let's go over here. The chunks are getting smaller and smaller every day. That's okay. Okay, so we have this. Now we have this state. Actually, let me translate everything such that y is at. Let's just put y at the origin. Maybe. Well, is that a bad idea? I mean, yeah. Let's just for now set y equal to 0, because we can always translate this picture anywhere we want. So now we are kind of quantizing around the origin of RD, and we are acting on this state where OJ is the primary and OI is the primary at X. Okay, and now we use this spectral decomposition to write this as a sum over K. So K is just runs over all the primaries. And we have some vector Vk which depends on X, right? So now Vk is some X-dependent vector which lives in this R delta K rho K. So far we haven't done anything, we just use this direct sum. But the key is that we can actually determine exactly what this Vk is as a function of X using conformal symmetry. Right, so what's Vk of X? Well, and of course Vk of X doesn't just depend on X, but also on I and J, but I'm suppressing that in the notation. So just imagine, well, you could put I and J if you want, but I'm not gonna keep writing all of that. So just remember that it also depends on I and J, not just on K and X. So what is the most general Vk of X? Well, we have a basis for this representation. So let's expand it in the basis. Let's write the most general thing. And so we have some contribution from the primary, which is some function times the primary. Then some contribution of the first descendants acting on the primary. Let me write in the next term as well. So this is at level 2, function of X, PB, OK. Yeah, so far I haven't done anything. I just wrote the most general. I mean, this is the most general state inside our Hilbert space, where these are just some functions. So A, N, I guess we have at level n, we are going to have some symmetric tensor of rank n, which is some real number which depends on X. You can, yeah, so the primary that depends on X is a translation. So we use a translation generator to enact with it on the primary at the origin. So that was this formula yesterday. So there was this formula yesterday that the primary at X is the same thing as e to the X dot P primary at the origin to the minus XP. So if you act with the primary at X on the vacuum, you're going to get the primary state. So now, okay, this is an operator, but this is a state, and you're going to get the primary plus plus x dot p, so xapa of the primary, plus so on, so xa xb, pa pb of the primary, and so on. Yeah, so this state has a Taylor's kind of expansion, and this is some state inside rho, but actually only if the norm of x is less than 1. So as long as the norm of x is less than 1, then this can be thought of as a state on the sphere. Otherwise, you're outside of the sphere and things break down. Yeah. Mm-hmm. I mean, yeah. I mean, the statement that O is a primary operator means that when x goes to 0, you get a primary state. So I mean, this is the primary state. So. Well, you can do it. So what's a non-primary operator? Let's take a derivative. Right. Now this is a descendant operator. You take a derivative, and this thing dies because there is no x. So then you have derivative here. So I mean, yeah, you can take any local operator, act with it on the vacuum, and ask what state do you get, and there is a definite answer. But once you know the answer for the primary, you know the answer for everything because you can take derivatives just like here.
The product of two operators becomes one of the operators acting on another state becomes when the circle you have drawn crosses the outer operator. So the circle is going through between the points.
The second thing. What was the second thing? Sorry? What's this? Can you repeat a question, maybe?
Yeah. So the product of two operators becomes one of the operators acting on another one. Passes through.
You're talking about this picture. Okay. So, yeah, in this picture we have a product of two operators. Yes.
Becomes one of the operators acting on another state.
Yes.
When the circle passes through between the 2 points, like it crosses the outer point.
When you have this picture. Well, sorry. If you have this picture, then the state that we have on the sphere is just something that lives in the irreducible representation of OJ. That's more or less, I guess, yeah, that's more or less what's happening here, right? So this insertion of this operator in a path effectively creates a state on the Hilbert space, like on this intermediate sphere. So that's this state, and then we are acting with OIX on that state and asking what state do we get on the sphere which encircles both of them, and that's this state. So this state is the one living outside. Okay, maybe let's take a break. After the break, we are going to fix all of these A's. All right. Before I talk a little bit more about the OPE, there is one thing that I forgot to say about the 3-point functions. So you may rightfully ask what happens for a 3-point function of 3 primaries which are not scalar. So if we had considered something like this, so OI is now is the primary of some spin, some representation of SOD, then what I said before is more or less still true, except instead of one constant, so we have 3 primaries, the most general ones, of 3 different scaling dimensions and 3 spins, rho 1, rho 2, rho 3. Then this is determined as a function of the axis and the indices. So as a function of all the three axes and A, B, and C, up to a finite number of constants. Number of real numbers. You know, the way to you can think of it representation theoretically, in a sense that you're trying to construct some trilinear functional, trilinear form of three representations. Basically, have a tensor product, roughly speaking, of three representations. Of the conformal group. And okay, so you want to construct a conformal invariant map from the product of three representations to the trivial representation, so just the one dimension, just complex numbers. And the answer is that such maps are just uniquely determined up to a finite number of constants. So this space is finite dimensional. I mean, this space of these maps is finite dimensional. Okay, I'm just not going to write it. And it's one dimensional when rho I, rho j, rho k are the trivial representation. In 2 dimensions, it's always one dimensional for any rho I, rho j, rho k, as we'll see tomorrow. And it turns out that this finite number of constants is exactly the same constants that we need to determine the A's exactly. So what are we trying to do? We are trying to construct these vectors vk, and that means that we need to find the coefficients of the primary and of all the descendants as a function of x, as a function of the indices. And what we are going to do is to focus on the simple case where, again, rho I, rho j, rho k are scalar, so the trivial representation. But the same reasoning will apply also in the most general case. Okay, so the idea is that conformal symmetry will determine these A's up to some finite number of constants. So let's see how that works. The idea is to take the conformal generators P, D, K, and M and act with them on both sides of the equation. So on one hand, we can act on the left-hand side. In that case, we know first of all how the generators act on O, because this is we know the representation of O, and we also know how the generators act on OI of X, because we wrote down some differential operators which represent how the charges act on these local operators. And at the same time, we can act the same generators on the right-hand side, where they are going to act on this VK, and they're somehow going to mix the various terms on the right-hand side, and then we can hope that actually things will be uniquely determined. So let's see how that works. We could start with the translation generator, but that one is actually not very useful because it's the only one which is not going to so D, K, and M annihilate O, and PA doesn't. So actually, P is not useful at the moment. But we can start with M. So if you act with MAB on both sides, so then on the left hand side, you're gonna get. So when you commute M through, it annihilates OJ because OJ is a scalar. So this is the same thing as just acting on the operator. And we know that that's, we have a formula for that. So that's delta x minus xb delta a, oix, oj. Okay, so when m acts on the left-hand side, we can replace it by this differential operator. Now, when MAB acts on the right-hand side, so let's focus, so let's act with MAB on VK of x. Well, VK of x is over there, and of course, MAB annihilates OK because OK is a scalar. So we get A0 of x times 0, because here, so this term just dies. And then we get some term like A1, and here MAB, so MAB hits this term, so we can commute, sorry, no, I shouldn't write, so this is C, and here's a commutator of MAB PC acting on OK, dot, dot, dot. Now we have a formula for the commutator. It's delta A C PB minus delta B C PA. Okay. So if you compare the two sides, so okay, maybe as an exercise. Sorry, let's just look at the first term. So you compare the action of this differential operator with this action. So you get that A0 is rotation invariant. So that means that A0 really only depends on the norm of x. Okay, instead of in the most general way, then A1 A1A needs to be proportional. So it has to be some constant. Let's call it constant. Well, so it has to be a rotation invariant thing times XA. Okay, so basically, as a vector, it needs to be proportional to the x vector times something times a scalar, and so on. So basically, rotation invariance tells you that all of the indices on all of the capital A's needs to come from XA, essentially. So that the general conclusion is that from rotation invariance is that each of these XA's is a function only of the norm times a product of the x's. Sorry, well, okay, this. Well, it's not really correct. It's a tensor which whose indices come only from the x's. It's some tensor whose indices either come from. It's a rotational invariant tensor, so the indices has to come from XA or from delta AB. So it's just something rotation invariant. So it's built out of indices, built out of XA and delta AB. But anyway, we are going to focus on the first two terms for now, or forever actually in this course. So just remember that A0 depends on the norm, and A1 goes like an X because there's delta AB has two indices. So delta AB only starts mattering once we have two indices. But you're encouraged to work this out to higher orders than I will show in the lectures. So that's the best way to understand it anyway. So okay, so we are focusing on A0 and A1. And we have used yeah. Well, so far they are not determined. They're just say with one index there is only with zero indices there is no tensor. With one index there is one tensor. With two indices there are two tensors. There's B and XA XB. You should make them maybe the same conformal weight, so write it like that. And so at 3 indices there is this one, and there is this one, and so on. So at every order there is some finite number of tensors, and their coefficients are for now undetermined. Okay, so we have used rotations, and we decided not to use translations. Now we use dilatations, so D. So when the dilatation acts on the left-hand side, is the same thing. So sorry, dilatation acts on this whole thing. It first acts on this operator, and then it acts on the state. So when it acts on the operator, you get x. That's from the formula for how it acts. So this is what we get from here. And from here we just, oh yeah, that's correct. OI, OJ. And from the second term, we just get plus delta J. Because when D hits OJ, just get a factor of delta J times the original thing. Okay. So basically when D acts on the left-hand side of the OP, then it acts like this differential operator. And when D acts on the right-hand side, so when it acts on VK of X, well, it just multiplies each term with n descendants by the scaling dimension of the term. So it's delta K times A0, which we know depends now only on the norm. Then the next term it multiplies by delta K plus 1, because it's a first descendant, so its scaling dimension is delta K plus 1. A1, A1 norm, XA, PA, okay, plus dot dot dot. Right, so here I've already used the rotation invariance to write A1 as a function of the norm times X. Okay, and now we need to compare the two sides, right? So we can act with this differential operator. If we act with this differential operator on this, sorry, on VK, we need to get the same answer, which fixes A0. So A0 as a function of X needs to be some constant. Let's call the constant C for now, times X to the power minus delta I minus delta J plus delta K. And A1, okay, so let's call this constant C0. Okay, I'm not being consistent with my notation. Sorry, C0, A1. This is some new constant, in principle C1, times the same factor times the same factor. Okay, so this is from scale. Basically, scaling determines the function of X. Scaling rotation determines the function of X, but there are still some constants. And if you proceed to higher and higher orders, then rotation and scaling will fix each of these up to a finite number of constants. So there's an infinite number of constants, right? Because at each level we have some finite number of constants, but there are infinitely many levels. But we haven't used special conformal. So let's use special conformal. And a special conformal is going to relate all of these constants, because that's the generator which moves us between the different levels. So let's actually do it explicitly this time. So let's act with Ka on both sides. So when Ka acts on the first term, we have this differential operator. Right, so this is from acting on Oi of x. And when Ka acts on Oj, what do we get? 0, right? It's a primary, so K annihilates it, so we just get that. Okay. And now let's act with Ka on the right-hand side. So let's just act on Vk of x. Well, it annihilates the first term because the first term is just a number times a primary. So it starts as follows. So we have this A1, which we called C1. There's some constant C1 times x to the minus delta minus j plus delta k. So I just copied A1. Okay, well, let's remember that the A1, okay, I think my notation is a bit lacking, but there's this XA, sorry, XB, KA, BB, acting on OK, plus dot, 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 right? So this XB is coming from here. But now we can use the commutator. So the commutator gives us what? Well, it gives us 2 delta AB D. And when D acts on OK, it becomes delta K. So in the end, we get something like C1, or not something we get exactly. This minus delta minus J plus delta K. Times 2 delta K XA. Okay, right, so from the first descendant term, we got a primary now. But on the left-hand side, we have this differential operator where the primary comes with a C0. Right, so this has to be equal to the differential operator acting. So when the differential operator acts on Vk of x, well, okay, I don't remember that by. But you get C0 XA x to the minus delta I minus delta J plus delta K. Times delta I minus delta J plus delta K. So this multiplies the primary. Right, so on the left-hand side, we get a C0. On the right-hand side, we get C1, multiplying the primary. So this allows us to determine C1 in terms of C0. We just compare this with that. This is just the times. So C1 is C0 times this delta I minus delta J plus delta K divided by 2 delta K. So far we have arrived at something like this, right? We are summing over all the representations. There is some C0, which depends on K. There's some X to the minus delta minus I minus delta J plus delta K. And then there's a primary. Then there is this constant. Delta K times XA, PA, OK, and so on. Yeah. The square bracket. The square bracket is this square bracket. Yeah. So I don't know. Maybe we should let's call it. Okay, it's okay. Let's call it K calligraphic. Okay. Okay, and you can probably convince yourself that if we had expanded this equation to all orders, then we could plausibly determine all of the coefficients here, which is indeed what happens. So at least if these two operators are scalar, and then rho k is also scalar, then there is only one constant in front, which is so far left undetermined. And for general 3 representations, there'll be some finite number of constants. And these constants are the same constants that we saw in the 3-point functions. Because so what's the well, how do we see that? We see it just by using this OPE to compute the 3-point function. Right, so now we can consider the 3-point function again, that we already know what it looks like. OI x1, OJ x2, OK x3. So the picture is the following. We have I guess we have OJ at x2, OI at x1, and OK at x3. And we imagine that we do this radial quantization centered around x2. So that creates some state on this sphere, which we can then think of. We can think of as a series of operators at the origin using this formula. Okay, maybe I should say a little bit more about it. So the same, the same formula written up for the state also has an interpretation as a formula about operators, where we just interpret the descendant state as a derivative of the operator at the origin. So OI, if I just rewrite the same formula for operators, I would get sum over K, K0. And now, so everything is translated. So I need to put x1 minus x2 to the minus delta I minus delta J plus delta K. And what do we have here? So we have OK at x2, because that's our origin of radial quantization, plus that constant and x12 dot, so let's see, this is x12a, I'm just going to put an upper index, with respect to x2, OK at x2, and plus dot dot dot. So we can just think of this as some very, very big differential operator. So let's just write this as 1. Yeah, I'm just going to put the OK outside. So plus dot dot dot, acting on OK at x2, right? So the way to think of it is that the kth term in the OPE is just a giant differential operator with infinitely many terms acting on OK at x2. And it's completely equivalent to the formula for states up there. So now we can use this formula for operators to compute the 3-point function. I mean, when are we allowed to use this formula? Well, we have derived it under the assumption that there are no other operators inside the sphere. So that's crucial, right? If there were some other operators inside the sphere, then we couldn't have done the manipulations that we did. We were assuming that these were the 2 only operators inside this unit sphere. But here it's okay. So we are imagining that x3 is outside. Sorry, which index? Yeah, right. So here we are summing over k, but here we are not summing over k. So here just OI, OJ, OK. So let's insert this formula into here. But then I guess we should call it k prime because we don't want to be summing over the same index that's fixed some value. So if we let's just keep the first term. So I just keep this term. And then we would get sum over k prime. So that's sum. There's a c k prime 0 x1 minus x2 to the power minus delta I minus delta j plus delta k. And now times the 2-point function of OK prime x2 OK x3 plus all of the other terms coming from the from this term and the dot dot dot. Okay, but this is a 2-point function, so we already know how to compute it, right? This is diagonal, so there is a delta k prime times x23 to the minus 2 delta k. So the answer for the whole 3-point function looks like ck0 x12 to the minus delta I minus delta j plus delta k x23 to the minus 2 delta k plus dot dot dot, and the dot 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 are getting smaller and smaller, so this is suppressed as x1 goes to x2, so as the norm of x1 2 goes to 0. So you can think of it that the OPE in this case provides us a power series expansion, power series for the 3-point function in the limit where x1 approaches x2. So the OPE is becoming kind of more and more faster and faster convergent as x1 approaches x2. And now you can compare, right? We have a formula for the 3-point function, which is completely non-perturbative exact for all x1, x2, x3. You can take it and expand it at small x1, 2, and compare with this expression, and you'll see that, first of all, the first term agrees, and second of all, the ck is just the Cijk that we saw earlier. Okay, so by comparing with the exact formula for the 3-point function, we conclude that actually the ck, that we call ck0, is just equal to thecijk from the formula for the 3-point function. Okay, so if you know all of these 3-point function coefficients, you also know all of these so-called OP coefficients. And just like we had some finite number of CIJKs, okay, so for general 3-point functions of general spins, we would have some finite number of these CIJKs. So let's call them CIJK alpha. Well, alpha goes from 1 to some number that only depends on the spins of the 3 representations. It's always finite. Then the same constants determine all of the OP coefficients. Yeah. Okay, are there any? So this concludes the discussion of the OPE. Yes? So C1, we related to C0. Oh, well, okay, it's in dot, dot, dot. So there is a, yeah, actually, there's another way to derive C1, which is just by expanding the 3-point function to the next order. And, yeah. So basically, the formula for the 3-point function is like a nice resummation for the OPE. In this way, to any order, you can determine all of the constants, the C1, C2, and so on. Yes. Suppressed as x12 goes to 0. So the OPE kind of has this form that at each, what happens at level n? At level n, you're going to have some x12 to a1 dot 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 x12 to an, acting on these descendants. Right, so this is the kind of term that you have at order n in the OP. If I had written out a dot dot dot, it would look like that, yeah. Theta x2 an on the OK x2. So this term is becoming smaller and smaller as x12 goes to 0. And the higher order you are at, the faster it becomes small. The faster it goes to 0. So that's how the OPE reproduces the series of the 3-point function. Yeah. Yep. Mm-hmm. Yes. Well, the delta functions are gonna be like x12 squared. Yeah. But the nth term is homogeneous of the same degree in x12. Uh-huh. Yes, actually, yeah, that's a very good question. It's not obvious, right? Because on the left-hand side, it's symmetric, but on the right-hand side, x2 plays a special role. But these terms, these coefficients, are exactly such that if you switch, then everything remains consistent. It's not obvious. So imagine if we switch x1, x2 here, we would switch x1, x2 here. So we would write this as x1, right? So what is OK at x1? Well, OK at x1 is the same as OK at x2 up to some descendants, up to x12, partial, OK at x2, basically. So just switching x1, x2 reorganizes this sum, but the differential operator is constrained in the right way such that this permutation preserves it.
So is the statement thatCijk is exactly ck0?
Yeah. Yes. That's exactly.
We're able to say that because we can take x1 to x1 to x2 because of scalar variance.
Well, we have a formula for the 3-point function, right? We wrote it down before, and you just take that formula and you send x1 close to x2, and you'll find exactly this timesCijk. I mean, the form. There is a formula x13.
Why are we not taking x1 to 0?
Hmm?
Why are we not taking x1 to 0?
Well, we are not taking it literally to 0. We are just doing the expansion at small x1. I mean, well, the OP is a statement about physics. I'm just making a statement about functions of 3 real variables. There's a function of 3 real variables, which is the 3-point function. And this function is analytic in x1, 2. Yeah.
So you're just comparing the value of the function for
Yeah. Yeah. Or in fact, for any value such that x1 and x2 is inside, such that the distance of x3 from x2 is greater than the distance of x1 from x2. Then that's the condition when the Taylor series converges. Okay. I was hoping to get to the bootstrap today. Okay, let's take 10 more minutes. Okay, maybe it's going to take less than 10 minutes. I don't know. Let's see. But I promise I will not exceed 10 minutes. So now we have we have some data. So far the data is the spectrum, so deltas and rhos, and the Cij case. And the point is that we can use this data to compute all endpoint functions. Right, so when you have a general endpoint function, in RD, so you have a bunch of points in RD, and now we can just sequentially do the OPE. As long as we always find, so we can, for example, do the OP of these 2 points. So that means we have to make sure that in the spheres that we are doing the OP in, there are no other operators. There's only just this one pair of operators. So you can do this OPE. This reduces the number of operators by 1, and in this way you can keep going until you have an infinite sum of 3-point functions. And the 3-point function you can evaluate because we have a formula for the 3-point function. Right, so let's just imagine that. Let's imagine we can do the OP of x1 and x2. So then we would have a sum over, let's say sum over k. And there's going to be something like ci1, ci2, k, and some big differential operator, which depends only on x1, 2. So it depends on what? It depends on I1, I2, and k. And then it depends on x1, 2. And it's a differential operator in x2. In xn. Yeah, so we have done the OP of x1 and x2. So from an endpoint function, we can write the endpoint function as an infinite sum of n minus 1-point functions. It doesn't matter. It's the same. I mean, this is just a number, right? It's a number which it's a number that depends on x2. No, it's not. This is just the path integral thing. It's like a bunch of insertions. They all commute with each other. Yeah. Just think of it as a statistical mechanical system where you're inserting the O's somewhere, and this gives you some function of x1, x2, x3, xn, which is permutation invariant. And then we are acting with a differential operator on that endpoint function. So no contact terms, no non-commutativity, nothing confusing. Okay, and in this way you can, okay, well, when does this converge? The claim is that this sum is going to converge precisely when there are no, when this is x2, this is x1, and if there are no other x's inside this ball. So if all of the other x's are outside. Okay, and now we can keep going and do this n minus 2 times, I guess. So that we, well, n minus 1, n minus 3 times maybe, so until we arrive at 3-point function that we can compute. Right? So in this way, any endpoint function is in principle determined by the CFT data. So this is an important term. So this is by the CFT data, which is the set of is the spectrum. So all the deltas and rows, and all the CIJKs, which I guess the CIJ. So the CFT data is this set. Right, if you know this set, not only that you can compute 2- and 3-point functions, but you can compute all endpoint functions using the OP. So in principle, all of the local data of your theory is determined by those numbers. Okay. But things get even better because this OPE can be done in multiple seemingly inequivalent ways. And they all have to agree.